This week we're going to be looking at some applications of, well, basically everything we've learned. So we're going to be looking at exponential growth and decay. It's something we learned about in Algebra 1 possibly, and in Algebra 2. It's where things are multiplying at the same rate each time. It's a geometric sequence, there have you. But what happens in exponential growth is that the rate of change is proportional to the value, to the quantity. Let's call it that. So most of the time when we're dealing with exponential growth or decay, we're dealing with time. Everything's with respect to time. So if we have, let's say our quantity was y, say our quantity is some kind of y, then the rate of change would be dy dt. Now let's look at what happens if the rate of change is proportional to that quantity. And when we mean proportional, we're talking about direct variation. That means that there's some constant k times that quantity. It could be, but we're multiplying by 2 each time, we're multiplying by 3 each time, whatever that is. Well, let's see what happens when we try to solve this differential equation. So, what will we do to solve this? Well, we try to get our variables on the same side. So, and this isn't a variable, this is a constant, this is some kind of multiplier. So I'll put this out. K is a constant multiplier. So if I rearrange this, I'd put dy over y equals k dt. Now we know how to solve a differential equation. We've done plenty of these. We're going to take the integral of both sides. Shoop, shoop. So the integral of dy over y, that's like having 1 over y. That's the natural log of y. And this would be kt, because that's some kind of multiplier, some kind of constant, plus some c. Now, ln is base e. So if I rewrite this, y equals e to the kt plus c. Well, I know by rules of exponents that's really e to the kt times e to some number, which, let's think about that. This is actually just some number, e to some number that we don't know. Well, I'm going to rewrite that as, let's call it another c. It's another constant, e to the kt. Let me give you an example, and you'll see kind of what happens. So I'm going to get an example. So let's take a a bacteria culture, which does grow exponentially. And let's say it starts with 500 bacteria, and after 3 hours, there are 8,000 bacteria. First off, let's see if we can come up with an equation to represent this. Well, I know it's going to follow this pattern. So let's see if we can find out anything with the first piece of information. It starts with 500. So at time 0, our y value is 500. Let's see where that helps us. So let's plug in that information. So 500 equals some constant e to the k times 0. Well, anything times 0 is 0. So I've got 500 equals c times e to the 0. Well, anything to the 0 power is 1, so c is 500. Would that work out every time? My initial value is always at time 0, so this is always going to be 1. Yeah, this c is always going to be the initial value. Nifty. Now I have to just find out that multiplier, what's happening. So maybe the other information would come in handy. So the other information says after 3 hours, so at t equals 3, we have 8,000. Okay, so I know c is now 500, so that means my equation is y equals 500 times e to the kt. So let's plug in this new information. Let's see if I can. There, that's better. So y would be 8,000 equals 500, that initial value, e to the k times 3. Well, I'm going to do two things here. I'm going to divide each side by 500 because that will clean this up a little bit. And I am being a little brain dead today, so 8,000 divided by 500 is 16. E to the 3k. So in our actual formula, we'd like to know what k is. So how do we solve this? Well, if we have e to the 3k equals this, well then that means that the natural log of 16 equals that exponent. That's kind of handy. So the natural log of 16 divided by 3 is my multiplier, that k value. So this will give me my full equation. My real equation is y equals 500 e to the natural log of 16 divided by 3 times whatever time I have. Once I have that equation, I can answer any question they give me. What if they asked, what's the number of bacteria after 4 hours? So what are they asking at 4 hours? How many bacteria do I have? Well, I'm just going to plug in 4 in there. So I would do 500 times e to the, and I want to keep this as exact as possible, so natural log of 16 over 3 times 4. 20,158. Wow. There's 20,158 bacteria. Well, what if they said, when, so that'd be like a part A. Part B, when does the population equal 30,000? Well, that means when does y equal 30,000? I don't know why I put that extra parentheses there. And all we have to do is solve the equation. So I would divide by 500. And that gives me 60 equals e to the natural log of 16 over 3t. Rewrite it as a logarithm. Natural log of 60 equals that exponent. So I would be dividing by that fraction, which means I would have t equals the natural log of 60 divided by that fraction would be the same as multiplying by the reciprocal. And I could find my time. Natural log of 60 times 3 divided by the natural log of 16. And I get my time as 4.43 hours. Don't forget your units on these. I'm going to add in one more example here. So the next example has to deal with half-life, and we have some kind of, what is this, radioactive material or something, and it deals with half-life. And that sometimes gets confusing to people, so let's think about what half-life means. Half-life means that this is the time it takes, so this is the time to have half the amount of material. So that means that's how long it would take from 50 milligrams to get down to 25. So let me write that little formula. That was the y equals some constant e to the kt. So that means if we started with 50, we would have 25, half of it, when this is our time. So what is that in decimal? That would be 0.002314 k. Could we find our k? Well, yeah. When I divide, I get 0.5 equals e to the 0.00014 k. Rewrite as a natural log. So the natural log of 0.5 equals the exponent over here. So our k would be the natural log of 0.5 divided by 0.00014. So our formula would be y equals 50 e to the natural log of 0.5 divided by 0.00014 t. So what if they asked when is the mass 40? So we're trying to find the time when the quantity is 40. Easy peasy. 40 equals 50 e to the natural log of 0.5 over 0.00014 t. And we'll just solve for t. So if I divide 40 by 50, I'll get 4/5, which is 0.8. E to the all that junk. Natural log of 0.8 equals the exponent over here. And now we can just solve for t, which would be to divide by that fraction, to be the same as multiplying by the reciprocal. And it's just basic calculations. The beautiful thing is that it always comes out this way on exponential growth and decay problems. So this one is a decay, the other one was a growth, and it's always going to come out to be these nice problems. So this is really negative 4.2 times 10 to the negative 4th. Try not to write it with E in there, and that would be in seconds.